Yeah. Hello, everyone. Thank you, Mr. Chairman, for giving me the opportunity to present our paper titled Performance Analysis of Improved Noise Cancellation Discrete Hartley Transform ACO-OFDM in a AWGN channel. I'm Dr. Max Frejus Owolabi Sanya, Assistant Professor at University of Abomey-Calavi in Benin. In this presentation, I will introduce the context of the study, the problematic, and the goal we address here. After that, I will present the methodology we use, the simulation result, and conclude. The exponential growth of services, high-speed internet, cloud computing, Internet of Things in communication networks has led to the pursuit of new alternative broad bandwidth capable of handling traffic and particularly high-speed data transfer. Like existing infrastructure becoming obsolete due to this increase of new services, optical fiber emerges as a strong candidate capable of overcoming the limitations of copper in achieving high-speed data transfer. Despite the high bandwidth capacity of optical fiber, various modulation techniques have been developed to optimize its use. This is the case of single carrier modulations and notably multi-carrier modulations such as orthogonal frequency division multiplexing, OFDM, which use multiple low data speed orthogonal subcarriers to transmit data at high speed. This is done by using an inverse discrete Fourier transform or fast Fourier transform. In optical systems, OFDM is shown to offer a potential low-cost solution. That is why for optical communications, several variants of OFDM is proposed, including DC-biased optical OFDM, asymmetrically clipped optical OFDM, and others modulation. Among these techniques, ACO-OFDM stands out as a promising approach, offering significant advantages in terms of power efficiency and robustness against interference. Some enhanced ACO-OFDM demodulators are proposed in the literature, but with high computational complexity or poor performances due to low cost noise or DC offset at the receiver. In recent years, one method that has garnered significant attention is the substitution of combination of the DFT block, discrete Fourier transform, in conventional OFDM systems with alternative orthogonal transforms include the discrete cosine or sine transform, the Walsh-Adama or the wavelet packet transform, and also the discrete Hartley transform. The aim of is to enhance system performance, such as reducing the peak to average power ratio, also called PAPR, or minimizing the bit error rates, or simply reducing the computational complexity. As the DHT, in particular, is notable for its real valued nature, requiring, only real arithmetic operations. This makes it especially suitable for real signal values, such as those used in binary phase shift gain, BPSK, modulations, and optical communication systems. Furthermore, the DHT and its inverse share an identical kernel, allowing for the use of the same circuitry in both the transmitter and receiver. This interesting property has received great attention in the literature and in our work. The goal of this work was how to improve the system performance of existing ACO-OFDM while reducing the computational complexity. That is why we try to do by exploring the performance of a new improved ACO-OFDM demodulation scheme based on DHT with pulse amplitude modulation that use both diversity combining and noise cancellation techniques in conventional ACO-OFDM. Our methodology is presented in the next slide. First of all, this slide shows you the modulation principle of conventional ACO-OFDM. At the transmitter, QAM, quadrature amplitude modulation symbols, are loaded on the odd index subcarriers with emission symmetry. The resulting signal after modulation via an inverse fast Fourier transform block is real and then clipped at 0 before transmission. This unipolar signal presents an anti-symmetry property as shown here. Figure 2 shows a block diagram of a discrete Hartley transform-based ACO-OFDM. At the transmitter, data is loaded on the odd index subcarriers without any kind of emission symmetry. The resulting signal obtained after the inverse discrete Hartley transform block is then clipped at 0 and sent over the AWGN channel. At the receiver, the modulation is processed and the data recovered on only the odd subcarrier after equalization. This slide shows you a block diagram of diversity combined ACO-OFDM demodulator based DHT. It has the same transmitter scheme as the previous ACO-OFDM based DHT, but at the receiver, the received and equalized signal undergoes a process where it is divided into its odd and even components. The odd component is then processed using an inverse discrete Hartley transform to obtain the information data from the odd scope carriers. This helps to estimate the DC offset as shown by equation 1, which is crucial for accurate demodulation and signal reconstruction using equation 2. The DHT improved noise cancellation ACO technique implements noise cancellation algorithm after the conventional DHT ACO-OFDM equalization. After this equalization, the symbols are modulated by an inverse DHT block, which leads to a time domain signal. According to the anti-symmetry property and zero clipping operation, we realize the virtual clean window process that can be simplified to a series of pairs detections between two hypotheses before DC offset with noise cancellation estimation, followed by a discrete Hartley block and the data recovery. This slide shows the principle of virtual clean window. Due to clipping at the transmitter, the ACO-OFDM signal contains many zeros, as shown by H0 and H1 in equation 3. In the presence of noise or DC offset, wrong decisions of these zeros can be made. To solve this problem, the virtual clean window uses equations 4 and 5 for DC offset estimation and noise cancellation. In table 1, we present the computational complexity of all the studied ACO-OFDM schemes. This is shown in terms of the number of inverse discrete Hartley transform or discrete Hartley transform blocks used. It can be seen that the proposed improved noise cancellation ACO-OFDM scheme offers advantage to use only one inverse discrete Hartley transform block compared to diversity combined ACO-OFDM. Figure 5 shows the simulation setup we implemented in order to analyze the performance obtained in a AWGN channel by all the schemes for comparison in terms of bit error rate versus electrical energy per bit to single-sided noise power spectral density ratio, simply called here by EP to N0. How the transmission link is modeled using MATLAB version R2021A. Simulations are conducted using 10,000 OFDM symbols. Each OFDM symbol is generated with an inverse discrete Hartley transform or discrete Hartley transform. Size use 512 subcarriers with 2 to 16 pulse amplitude modulation mapping constellation, compared to the traditional IFFT or FFT block used in OFDM with 4 to 250 QAM constellation. Cyclic preface of 128 samples was used. Bit error rate, mean BER performance, is estimated through Monte Carlo simulation by counting numbers of errors per transmission. A comparative study between conventional ACO-OFDM and ACO-OFDM technique-based DHT is shown by figure 6. We can see that BER improves as SNR increases. This can be explained by the fact that as the SNR increases, the transmitted signal becomes less affected by noise, resulting in more accurate symbol transmission. Also, for any pulse amplitude modulation size with the discrete Hartley transform ACO-OFDM technique, we observe similar performances as the conventional M-square quadrature amplitude modulation ACO-OFDM. As the spectral efficiency of M-PAM constellation is equal to M-square QEM constellation using emission symmetry, it is clear that the transmitted M-PAM or M-square QEM signals experience similar level of noise impact. Moreover, at a fixed EB to N0, we observe that the BER deteriorates when constellation size increases. Hence, we showed as many authors that ACO-OFDM based discrete Hartley transform can achieve similar BER performances as conventional ACO-OFDM, but with low power consumption. Figure 7 presents a comparative study between this diversity combined ACO-OFDM and ACO-OFDM based DHT in terms of electrical EBN0 and comparable spectral efficiencies. It can be seen that diversity combined ACO-OFDM can offer an approximately 3 dB gain in SNR compared to ACO-OFDM at a fixed BER and constellation size. These results to the improved demodulation offered by diversity combining methods in presence of noise and DC offset. Figure 9 presents a comparative study of improved noise cancellation ACO-OFDM with diversity combined ACO-OFDM based DHT, focusing on the electrical EB N0 and comparable spectral efficiencies. It can be observed that both techniques achieve similar BER performances with an approximately 3 dB gain in SNR compared to conventional ACO-OFDM as shown by figure 8. This improvement is due to the effective demodulation provided by both diversity combined and improved noise cancellation at the receiver. Both demodulators reduce the system noise impact by approximately half. Since the improved noise cancellation ACO-OFDM reduces computational complexity of diversity combined ACO-OFDM method by removing one inverse discrete Hartley transform block while preserving the same BER performances, it stands out as a promising candidate for improved ACO-OFDM modulation for optical systems. In conclusion, this study has investigated and proposed an efficient ACO-OFDM demodulation approach that improves the BER performance and computational complexity of the ACO-OFDM technique through the use of the discrete Hartley transform and pulse amplitude modulation. Combining PAPR reduction techniques with the proposed improved noise cancellation ACO-OFDM based DHT could be the next step for our studies. Thank you very much for your kind attention. We are open for